Okay, so in the last class, we were discussing convergence of sequences of random variables, and we saw three different notions of convergence. So mainly we examined two notions of convergence. One, what we called almost sure convergence, or strong convergence, or convergence with probability 1. And we said that a sequence xn converges almost surely to x if asymptotically the probability of the limit as n tends to infinity of xn is not equal to x is equal to 0. Or another way of putting it was that if we define this event am as the event that for all n greater than or equal to m, xn is close to x, is epsilon close to x, then the limit as m tends to infinity, probability of am is equal to 1. Okay, and we saw three different examples. One where x1 is uniformly distributed in 0, 1, and xn is x1 raised to the n. We saw that this sequence of random variables, it converges to 0 almost surely. And then we saw another example where you have a sequence of random variables where each xn is Bernoulli 1 over n. Right? They're all IID, but Bernoulli 1 over n. And we saw that this sequence of random variables does not converge almost surely. And there's also, and as an exercise, I asked you to look at the following sequence of random variables, x1, x1, xn, and so on, which are IID uniformly distributed over 0 to 1 plus 1 over n. Right? And the question was, does this converge almost surely to a random variable which is uniformly distributed in 0, 1? Okay, so has anyone tried it out? Does this converge almost surely? Anybody? Okay, so if you've not tried it out, you should definitely do it today. Just try it out. You try to use the same approach. Compute the events am and try to find the probability of am. So generally, not just in this problem, when you want to check whether a sequence of random variables converges almost surely, here is a sufficient condition. It's not necessary, but if you look at the events, let me call them Bm, which is the event that, let me call it Bn. So if I define the event Bn, and Bn is the event that xn minus x is less than or equal, is greater than epsilon. Okay, so if event am is to happen, then none of the events Bn for n greater than or equal to m must happen. Do you agree? So an occurs only if none of Bm for m greater than or equal to n occurs. Right? And the goal is to show that limit as n tends to infinity, probability of an equal to 1, or the probability of an complement equal to 0, right? And that happens if you can show that limit as n tends to infinity, probability of union m greater than or equal to n of bm, this is equal to 0, right? So if you can show that, now you computing this probability, the probability of this union may be difficult, but sometimes what you can do is look at the limit as n tends to infinity, just use the union bound to take the summation from n to infinity, probability bm. So if you can show that this limit is equal to 0, then you're done. All right. If you cannot prove, if you can show this, then it's sufficient to show that the sequence converges almost surely. Right? So this is one approach. If you can somehow prove that this is equal to 0, then that's good enough. All right. Okay. So in addition to convergence almost surely, we also saw convergence in probability, and this is a weaker notion of convergence than almost sure convergence. So convergence in probability says that the limit as n tends to infinity, the probability that xn minus x is greater than epsilon, this should be equal to 0. Right? So for sufficiently large n, the probability that xn deviates from x by an amount epsilon is sufficiently small. All right. So in comparison, if you want to show almost sure convergence, then basically the limit is inside the probability, whereas here the limit is in some sense outside the probability. All right. So difference between 1 and 2, are you talking about examples 1 and 2 or the two different notions of convergence? So you mean almost sure and convergence and probability? Right. So as I mentioned, in convergence and probability, basically the limit is outside this probability. Okay. Whereas in almost sure convergence, the limit is inside this probability. So what can happen? Okay. So again, this is I'm going to be a little loose when saying what is happening. So you have x1, x2, and so on, right? So if the sequence converges almost surely, there'll be some point in time, that is, there'll be some m beyond which, if the sequence converges almost surely, then there'll be some point beyond which xn minus x is greater than epsilon. So the probability of this happening for all n greater than or equal to m. So this will be probability that this is less than epsilon. So this will be close to 1. So beyond a certain m, all the xn's beyond this point will be close to epsilon. And that is what happens if the sequence converges almost surely. If the sequence converges in probability, this may not happen. There could be many n's beyond which, so for every m, you could find infinitely many n's beyond this point for which this is not satisfied. But the limit of this probability could still be equal to 0. So as I mentioned, if you look at this particular example, so this example is helpful. So take a look at xi. So the probability that xn is equal to 1 is 1 over n. And the xn's are all IID random variables. Right, so take x1, x2, xn, and so on. Right, the probability that xn is 1 is 1 over n. So if you pick any particular location m, all right, so firstly, as n tends to infinity, the probability that xn equal to 1 is 0, and the probability that xn is 0 tends to 1. Right? So firstly, it's clear that this sequence converges in probability to 0. Is that much clear? It satisfies this particular definition. Do you agree? Right. Okay, so certainly this, in this example, where xn is IID Bernoulli 1 over n, this definitely converges in probability. So that is fine. So the question is, the main point here is that this sequence does not converge almost surely, that it does not satisfy the properties of this particular definition over here, of this definition over here. And basically what is happening over here is that, let's look at any particular location m. Okay, any particular location m, and look at the sequence beyond m. Okay, so x m plus 1, x m plus 2, and so on, right? So all of these are IID sequences. Okay, so sorry, these are all independent but not identically distributed. My bad. So these are all independent random variables, not identically distributed. The probability of each of these being 1, so probability of xm equal to 1 is 1 over m. The probability that xm plus 1 is equal to 1 is 1 over m plus 1, and so on, right? But what is the probability that all of these are going to be equal to 0? Right? So if you fix any particular location m, what is the probability that everything beyond that point are all zeros? Is it m minus 1 or m minus 1 by n? Are you sure? So note that these are all independent random variables, right? So what is the probability that xm equal to 0? It is right, 1 minus 1 over m, correct? 1 minus 1 over m, the probability that xm plus 1 is 0 is 1 minus 1 over m plus 1. Yeah, so the probability that xm to xn are all 0 is m minus 1 divided by capital N. So the probability that all of them are going to be 0 is equal to 0. Right? xm equal to 0, xm plus 1 equal to 0, and so on. Everything beyond this point is 0. So the probability of this happening is equal to 0. So therefore, it does not converge almost surely. But if we want almost sure convergence, if we demanded that this particular sequence had to converge almost surely, then we would have demanded that everything beyond this point is equal to 0, which is not happening over here. All right, so therefore this does not converge almost surely. So the notion of almost sure convergence is different, and in fact is stronger than convergence in probability. Is that clear? Any questions? So there's one more weaker notion of convergence, which we'll briefly look at, and that is convergence in distribution, or sometimes called weak convergence. So we'll say that a sequence of random variables xn converges in distribution to some other random variable x if the limit as n tends to infinity of the CDF is equal to the CDF of x. So as long as the CDFs converge to the CDF of x, and this happens, and this need not happen for all points in the real line, as long as it happens for all points except for points of discontinuity, at points of discontinuity, right? As long as this happens, we're good. So we'll say that the sequence converges in distribution to x. Okay, so here this is a requirement only of the CDFs, or it could also be in terms of the PDF. So if the PDF converges to the PDF of x, that is the PMF of x if the PMF of xn converges to the PMF of x, then we say that the sequence converges in distribution. Okay, and again, at the face of it, it may seem like all these notions are almost the same, but the best way to understand the difference is through these three examples. All right, so we have these three examples over here: example 1, example 2, and example 3. Okay, and that's why I want you to fill out this particular table. So you have example 1, example 2, example 3, and we saw three different notions of convergence. Almost surely, we saw convergence in probability and convergence in distribution. We know that example 1, this converges almost surely. Example 2, it does not converge almost surely. And example 3, well, you have to verify. So what about convergence in probability? We saw that example 1, this does not, this converges in probability. You can show that. Example 2 also converges in probability. Example 3, I want you to check and find out if this converges in probability or not. I also want you to check whether these three these three sequences converge in distribution to the respective random variables. Okay, so example 1, if it converges, it should converge to 0. So it's a distribution which puts probability 1 on 0. So x equal to 0 with probability 1. Example 2 is also the same thing, x equal to 0 with probability 1. Example 3, x is uniformly distributed over 0, 1. Okay, and you have to check whether the sequence of random variables given to you converges to the respective x and almost surely, or with probability, or in distribution. Okay, so I'll leave this as a homework. And it's really by working out these examples that you get to know the subtle differences between these three notions of convergence. All right, so these three notions are indeed different. And in fact, there is uh, it is possible to formally show the following. So if a sequence converges almost surely, then it will converge in probability. You can show that. And if a sequence converges in probability, then it will always converge in distribution. But in general, the reverse is not true. So there are sequences. Just work out these examples and you will see for yourself. So there are sequences which converge in distribution but do not converge in probability. And of course, there are sequences which converge in probability but do not converge almost surely. Okay, so this is strictly stronger than convergence in probability, and convergence in probability is strictly stronger than convergence in distribution. All right. Any questions? Okay, so let's see a couple of theorems that you would have seen in a course on probability and random processes. Okay, so you would have seen the following. So the weak law of large numbers. Of course, the weak law of large numbers holds for slightly more general sequences of random variables. But in particular, if x1, x2, and so on, if you have a sequence of random variables which are IID and they have a finite mean, then the sample mean, so 1 over n summation I going from 1 through n of xi, this converges in probability to the expectation of x. So for example, when you say that you want to toss a sequence of coins, so you have a coin and you toss it n times, you know that for sufficiently large n, then the fraction of heads, if it's a fair coin, then the fraction of heads is going to be a half. Right, so the weak law of large numbers, or more generally the loss of large numbers, make these statements more formal. So in what sense is the sequence of coin tosses, or the fraction of heads, equal to the probability that head equal to 1, which is equal to half. Right, so if you take a biased coin where the probability of getting a head is maybe alpha, then the fraction of heads is going to converge to alpha, right? So the weak law of large numbers in particular says that this convergence happens in probability. So more formally, it says that the limit as n tends to infinity, the probability that 1 over n summation I going from 1 through n of xi minus expectation of x, the probability that this is greater than epsilon in the limit is equal to 0. Okay, so let's try to prove this. We won't prove it in general because that is a little harder, but it's easier to prove it for random variables which have a finite second moment. Okay, so we'll assume that the expectation of x1 is equal to mu. So they're all IID, so the probability of any, so the expectation of any of the xi's is equal to mu, and this is less than infinity. And we'll also assume that the variance is finite. So the expectation of xi minus mu the whole squared, this is equal to sigma square, and we'll assume that this is less than infinity. Okay, so given these assumptions, we want to prove that the sample average, 1 over n summation I going from 1 through n of xi, this converges in probability to the expectation, which is mu. Okay, so any thoughts? How would we show this? We want to basically prove this statement over here, right? So what can we use to prove it? Can we use some of the tools that we've already studied in the previous class? Okay, inequality. What inequality? Exactly. So you can use Chebyshev inequality, right? Uh, so the quantity that we are interested in is the probability that 1 over n summation I going from 1 through n of xi minus expected value of x is greater than epsilon. Okay, so if I call this random variable y, then what is the expected value of y equal to? So if y is 1 over n summation I going from 1 through n of xi, then what is expectation of y? Exactly. So it's equal to mu, right? So it's equal to expectation of whatever x1, which is mu. Okay. And what is the variance of y? These are all IID. The xi's are all IID. So what is the variance of the summation of xi divided by n? Exactly. So it's the variance divided by n, right? So it's the variance of 1 over n summation I going from 1 through n of xi, which is 1 over n square times the variance of the summation, which is n times the variance of xi, which is n sigma square. So it is sigma square divided by n. Correct? So that is fine. So therefore, just by using Chebyshev's inequality, we know that this is less than or equal to the variance. So this is basically probability that mod y minus expectation of y is greater than epsilon. So this is less than or equal to the variance of y divided by epsilon square, which is sigma square divided by n epsilon square. Correct? And as n tends to infinity, this just tends to 0 as n tends to infinity. So the limit as n tends to infinity of this probability is equal to 0, right? And therefore, the summation or the sample average converges in probability to the expectation of x. Right? So, any questions? So this is a simple proof of the weak law of large numbers for the specific case where both the mean and the variance exist, right? And they're finite. But then you could also have sequences of random variables where the mean is finite, but the variance is infinite. And even then, the weak law of large numbers holds. But that requires completely different tools. All right. So any questions? Okay, so this is what we call the weak law of large numbers. So there's also a strong law of large numbers. All right, and under the same conditions. So if x1, x2, and so on are IID, and the expectation of xi is finite, then the sample average I going from 1 through n of xi. So this converges not just in probability, it actually converges almost surely to the mean. Okay, so the sample average converges almost surely to the true average, and this convergence happens almost surely. Now these assumptions are generally not enough. So if you want a simple proof, then these two assumptions are not good enough. So if you try to invoke Chebyshev's inequality directly, then you cannot prove that the convergence happens almost surely, right? Because why does that happen? Because if you want to show almost sure convergence, one way to show it is to try to bound summation whatever m equal to n to infinity the probability of bm, or in other words, the probability that 1 over m I equal to 1 to m xi minus mu is greater than or equal to epsilon. So I want this to happen. So I want so the probability of an is upper bounded by this quantity, and if you can show that this summation converges, so if this tends to 0 as n tends to infinity, then we are done. So we can show that this convergence happens almost surely. But then if we just use Chebyshev's inequality, this quantity is basically sigma square divided by n epsilon square, but summation m going from n to infinity of 1 over n, this does not converge to 0, right? In fact, it converges to so in fact this summation would diverge. One over m, sorry, this would be m epsilon square. So this does not converge to 0. This is equal to infinity, and therefore we can't really prove the strong law of large numbers with just this assumption. But then if you have stronger assumptions on this, then it becomes very easy. So in particular, if you can somehow prove that this this quantity is upper bounded by even sigma square, or instead of order 1 over m, if you have an order 1 over m square, then this converges to 0. So in particular, I want you to solve the following homework. So if x1 and x2 are so on are IID Bernoulli P, then I want you to show the strong law of large numbers. So essentially 1 over n summation I going from 1 through n of xi, this converges almost surely to P. All right. And once again, so So these are two statements, one which deals with almost sure convergence, one which deals with convergence in probability. And if you've seen the central limit theorem, then that is a statement regarding convergence in distribution. So if you take a sequence of random variables and you look at, if you have a sequence of n IID random variables and you look at summation I going from 1 through n, xi minus n times mu divided by n sigma square, then this quantity converges in distribution to a Gaussian. All right. So if x1, x2, and so on are IID random variables, then yn, which is summation I going from 1 through n, xi minus n times mu divided by n sigma square, this converges in distribution to the standard Gaussian. All right, and this is just the central limit theorem. So you may have seen this in a probability course, and this is really the formal statement of the central limit theorem. Sorry, Chandramuli. So which summation in probability are you talking about? Oh, are you referring to this particular term over here? Right. So in strong convergence, you want to show that this probability, right? So this probability converges to 0. So basically, everything beyond position n is less than or equal to epsilon. Okay, or beyond location n, nothing is greater than or equal to epsilon. All right. So sorry, this should have been an complement. So the probability of an complement is basically the probability that 1 over m summation I going from 1 through m xi minus mu is greater than or equal to epsilon for some m which is greater than or equal to n. So an does not happen if for some position n greater than or equal to m, this condition is violated, right? Or this happens. It is not less than or equal to epsilon. Correct? But basically the event within these brackets is a union of infinitely many events. So it is basically the union for all m greater than or equal to n, that whatever the summation 1 over m summation xi minus mu is greater than or equal to epsilon. All right, and we can just use the union bound to write it as the sum of the probabilities. Right? Is that clear? So this is for almost sure convergence, not convergence in probability. So convergence in probability requires that just this particular probability converges to 0 as n tends to infinity. And almost sure convergence, of course, it is not necessary that this happens. It is sufficient that this happens, right? So it demands that this probability falls down really, really fast. Okay? So it can't fall down slowly. All right. Okay, good. So this is the, so these are the two laws of large numbers, and there's also the central limit theorem, which you would have seen in a probability course. We won't really be using the central limit theorem in this course, but it's a good thing to know. So when you say that the summation of IID random variables is close to a Gaussian, you should know exactly what you mean by it being close to a Gaussian. Because if you take just summation overall IXI divided by n, then this converges to mu, right? But then if you appropriately subtract the mean and divide it by n sigma square, then, sorry, this should be square root n sigma square. So if you normalize it appropriately, so note that here the normalization is with respect to root n, unlike this case where the normalization is with respect to n. Right? So this converges to a Gaussian, whereas this converges to a constant. Right? So summation 1 over n, 1 over n summation xi, this converges to a constant. Of course, it's in the almost sure sense, whereas sort of 1 over root n summation xi minus n mu, this converges in distribution to a Gaussian. Right? Okay, so that wraps up our discussion on at least the basics of probability. So now we can actually get to the real information theory part. So in this class and the next, we'll do a quick review of topics in information theory of various notions that you would have already studied. I will not prove many of the statements. You can just go through the textbook or revise your notes or look at the lecture videos on information sciences and information theory. But I'll still skim through the definitions just to make sure that you remember them. Right? So we've seen two concepts in information theory. One is source coding and the other is channel coding. We dealt with those two problems, and associated with both these problems, we saw different information theoretic quantities. So given any random variable x with a probability mass function, any discrete random variable x with a probability mass function px, we define the entropy of x, or actually the entropy of px, as this particular quantity. So it's a summation overall x, px log 1 over px, and logarithms are taken with respect to base 2. Okay. Another way of looking at the same quantity is the following. So if you think of x as a random variable, if you look at log 1 over px of x as a random variable, then the entropy is basically the expectation of log 1 over px of x, where this x here is a random variable. Right? And this follows just by definition. So the expectation of this random variable is summation p of x of this, and that is just equal to the entropy, right? And you can define the entropy not just for a single random variable, but also for two random variables, or in general, multiple random variables, n random variables. And the entropy is defined exactly in the same way. So the entropy of a joint distribution is the summation overall x and y, p of xy log 1 over p of xy. All right. And similarly, we defined, so the, at least the intuitive interpretation of entropy is that it's a measure of randomness in the random variable. So the higher the entropy of a random variable, in some sense, the more information content it possesses, or the more random it is. Because, for example, if x is totally uniform, right? If you have a random variable with finite support and it's completely uniform, then the entropy is maximum. If it is not uniform, then the entropy will be lesser. And in particular, if it is deterministic, so the probability, so if all the probability mass is put on one particular point, then the entropy is equal to 0. Right. So that's like, again, it's a heuristic or an intuitive way of thinking about entropy. It's not formal, right? But there is a more formal definition of entropy, and it comes naturally in the problem of compression. Right. So similarly, the conditional entropy of two random variables. So the conditional entropy of x given the random variable y is in some sense the amount of uncertainty left in x when you already know y. Right. So for example, if x is a function of y, then the conditional entropy of x given y is equal to 0 because there is no more uncertainty left in x. Right? And similarly, if x and y are independent, then the conditional entropy of x given y is equal to the entropy of x because uh, because because the uncertainty does not reduce if you give y. But in general, h of x given y is less than or equal to h of x. So conditioning can only reduce entropy, it cannot increase entropy of x. And you have equality if and only if x and y are independent. Right? And of course, all of these quantities, the conditional entropy, the entropy, are all greater than or equal to 0. All right. We've also seen, so given two distributions, the KL divergence or the Kullback-Leibler divergence or the relative entropy between those two distributions is given by this particular quantity. So it is the summation over all x in x of p of x log p of x over q of x, right? And we've seen that the KL divergence is always non-negative. So it is greater than or equal to 0, and it is equal to 0 if and only if p of x is equal to q of x for all x. So that is why we call it a divergence. And in some sense, it's a measure of, or it quantifies how different the two distributions are. All right. So in our information sciences, information theory course, we've also seen the source coding theorem, which gives an operational meaning to entropy. Right? So if you have a sequence of random variables, x1, x2, up to xn, and these are IID distributed according to px, then the source coding problem asks for the best compressor for compressing x. So essentially, we want to design a compressor and a decompressor, or an encoder and a decoder, such that you can represent xn using a very small number of bits. So in particular, let's say the sequence of length n should be represented using kn bits. Kn, and in addition, the decompressor should be able to recover xn with an arbitrarily small probability of error. Right? So that is the source coding problem. And Shannon's source coding theorem says that if xn is IID distributed according to px, then for every epsilon greater than 0, we can find a sequence of compressors and decompressors such that the probability of error is vanishing in n, and the rate, which is kn over n, is asymptotically close to the entropy. So for every epsilon greater than 0, we can make it arbitrarily close to the entropy. We can make it epsilon close to the entropy. All right. So this is only the achievability part of the source coding theorem. So it says that the achievability part says that you can construct compressors which achieve this particular bond, but there is also a converse which says that or that if you try to compress at a rate below the entropy, then you cannot do it. You will have to pay a penalty. So the probability of error will be large, right? So that is why this is called an achievability result. It tells you that you can construct compressors which achieve this bound, and the converse, or sort of an impossibility result, says that if you try to compress it at a rate below this bound, then you will have to pay a penalty. The probability of error will be large. And in fact, you can prove an even stronger statement. So there is something called a weak converse in information theory, which says that asymptotically the probability of error will be something which is greater than or equal to epsilon. So you cannot make it go down to zero. It has to be bounded from below by a constant. And you can prove an even stronger result, which is sometimes called a strong converse. And this says that the probability of, so if you try to compress at a rate below the entropy, then it is not just that the probability of error is greater than zero, the probability of error is in fact equal to 1 asymptotically. Right? So that is what Shannon's source coding theorem says. And this is for a single source, and you want to just compress an IID source, right? And you can prove this for more general distribution. So in fact, as long as you have a stationary and ergodic sequence, then you can compress it at a rate close to the entropy rate of the source, and you can prove similar achievability and converse results. So although we will be dealing with mostly IID sequences in this course, and also in our previous course on information theory, these results hold for much general sources. So you can compress a sequence to a rate close to the entropy rate, and it's impossible to compress at a rate below the entropy rate. And this holds for IID sources, it holds for kth order Markov sources, it holds in general for stationary and ergodic sources. Right? And then we also defined the mutual information between two random variables. And there are, again, different ways of writing the mutual information. One way to write it as is using the KL divergence. So it is a KL divergence between the joint distribution of x and y and the product of the marginals of x and y. And it can also be written as the difference between the entropy of x and the entropy of x given y, and similarly the entropy of y minus the entropy of y given x. Right? And the interpretation, the intuitive or heuristic interpretation for mutual information is how much information about x is given by y, or how much information about y is given by x. And again, heuristically, you can interpret this particular statement in this using this interpretation. So the amount of information about x given by y is the amount of uncertainty in x minus, or the total information content of x minus the amount of uncertainty, or the amount of residual uncertainty left in x having observed y. Right? So the information about x contained in y is the total uncertainty in x minus the amount of uncertainty that remains after having observed y. So that is the amount of information that you get about x after seeing y. All right, and you can, and this is an operational quantity which appears when you talk about the channel coding problem. So we'll see this in the next class. Are there any questions? So before the next class, you should maybe quickly revise your notes on information theory. You can also go through the Cover-Thomas textbook to see what you've already learned. All right, any questions? Okay, so we'll meet in the next class.